So good afternoon and welcome to Purdue University for the CERIAS Security Seminar. Our speaker today is Abe Clements. Abe is a PhD candidate here at Purdue University, but we are lucky to have him back here at Purdue to continue his education because for the last several years, he has been a full-time researcher with Sandia National Labs, working within this focus area. So I'm not sure whether we say, here's one of our bright students, or here's one of our strategic partnership members. In this case, it is both. So please join me in welcoming Abe back to campus for his technical talk.
Thanks. So just as Joel said, I'm a PhD student here on campus. Sandia has a doctoral studies program that I was a participant of that they sent me here to campus to work on PhD. I'm still here on campus while I work full-time for Sandia, and I'll be presenting some of my research that I've done with my PhD today. Also, just a short plug, we are starting an internship center here on campus for Sandia National Labs, looking to hire Purdue students for year-round interns. So if you're interested in that, please talk to me afterwards, or Ken, who's sitting in the back. So today I'm going to present two of my papers. The first one was for in IEEE Security and Privacy from 2017, and the next one was in Usenix last week. So my work, the first paper is projecting bare metal embedded systems with privilege overlays. This was work done by myself, Naif, Khaled Prashast, Jinkyu, and Saurabh Bagchi and Matthias Pear. Dr. Bagchi and Matthias Pear are my advisors. So I work in bare metal systems. So a bare metal system is a system without an operating system. They often found on microcontrollers and very small systems. They're constrained. We're talking about systems that use a megabyte of flash and a couple kilobytes of RAM. And then they have really tight runtime constraints and low power requirements. And because there's just a single application on there, there's no separation between kernel or user space. Some examples of systems that are built kind of like this are Amazon's dash buttons, some smart locks, engine controllers. Within a micro SD card, there's a microcontroller. There's a bunch of flash in a microcontroller. That microcontroller is running bare metal code. Some people have actually rewritten that firmware and exploited essentially SD cards. Wi-Fi system on chips. So your cell phone has a system on a chip in there that handles all the low-level Wi-Fi. It's running bare metal code. These systems, security is simply just left out. They're so constrained, they're so small, security has just been left out. So as I go through my talk, I have this diagram, and it has the different parts of these systems. At the top, you've got hardware, some security hardware. They have some very primitive hardware security features. There's some I/O, some of which may be sensitive, some of which may not be sensitive depending on the application. There's RAM, which will have your global data, your stack, heap, and your flash. It's down in where your code is stored. As I go through my talk, we'll talk about how this approach we call EPOXY builds up defenses on these constrained systems. So right now, you've got a single root execution domain, and you've got the security hardware. It's untrusted or trivially bypassed. It's all controlled by memory mapped I/O. So by writing a particular address in memory, you can turn it off. It's always accessible. Sensitive I/O is always accessible. Your stack and your global variables are subjective to stack smashing, code injection, global data corruption, and your code has no ROP or code reuse defenses. So some of the challenges with applying defenses in this space is there's a single application, and there's no separation of privileges. Everything's essentially root. They lack a memory management unit, so most of your protections on your desktop use the memory management unit to set permissions on pages of memory. We don't have any sort of virtual memory in this space. We only have physical memory. They have small memory sizes, so any defense we deploy has to be very lightweight. And then they have these tight runtime constraints, so there's not extra processing power that we can devote to security. So our approach here is EPOXY. We call it Embedded Privilege Overlay across X hardware for Y software. Really, it's a fancy way to make the name EPOXY work. So LLVM, it's an LLVM-based compiler. So LLVM is a compiler framework, a cross-compiler framework. We modified it to instrument the program. So it provides protections for code injection, control flow hijacking, data corruption, and manipulation of sensitive I/O. We do this using a technique we call privilege overlays. which creates two levels of privileges, a privileged and unprivileged, and this is the foundation for all of their defenses. Let's talk a little bit about what the threat model we're working under. So whenever you're doing a security paper, there's always the threat model. How's somebody going to attack this? How am I protecting against it? So the threat model here is, we're assuming the attacker has an arbitrary memory corruption, so they can rewrite any part of memory they want, and that their goal is to obtain execution or corrupt specific global variables. They, however, do not have access to the physical system. So we're assuming they can't access the physical system, they can't read off the firmware on that system. We require a couple of hardware support. We require separation between a privileged and an unprivileged mode. A memory protection unit. This is, instead of a memory management unit, the memory protection unit allows setting privileges on specific regions of physical memory. So I can set read, write, and execute permissions on a limited number of physical memory regions. And we also require that memory usage can be determined a priori. This means that I know how much memory my application is going to use before I start running it. These three constraint requirements are all commonly available on embedded systems. If you're operating on physical memory, you have to know how much memory you're going to use before you run your application, otherwise it's not going to run. And modern microcontrollers such as the ARM Cortex-M series microcontrollers have a memory protection unit and the separation of privileges. So here we're back to our application. Before any protections are put in, everything's privileged execution. We're going to first apply what we call privilege overlays. So what privilege overlaying does is it creates a privileged and unprivileged code, but it allows the developer to assume that they can read and write anywhere in memory. They can develop just as they have been in the past, as if everything's just got privileges. But then at runtime, we're going to restrict some operations. We're going to restrict most of the application to unprivileged and allow only a few operations to be done with privileges. So the way we'll do this is we use static analysis of the program to identify the parts that actually need privileges. And there's two things that need privileges. There's some instructions defined by the instruction set architecture that have to execute with privileges, such as enabling and disabling interrupts. It's a privileged operation. If you execute it without privileges, it's just ignored. So we have to make sure that these instructions operate with privileges. The other thing that may happen is there's some parts of memory, such as the memory protection unit, that have to have privileges when they're read and written. And so what we do is in our static analysis, we identify these instructions and these memory accesses that require privileges. And then we're going to add code to elevate just those privileges. So this allows us to apply DEP, or data execution prevention. So the problem before is the memory protection unit allows us to apply data execution prevention, but we've got an arbitrary memory write, which can just turn off the memory protection unit. So first we kick everything out of privilege mode, and I'll build this up. Then after kicking everything out of privilege mode, we configure the MPU to enforce data execution prevention. And then just elevate these few things that actually need privileges. So here, I'll go through an example here. So here's their application here on the left. We're going to say that accessing this UART is sensitive. So we're going to use the memory protection unit to restrict its access to only privileged code. So the first thing we're going to do is we're going to kick the whole program out of privilege mode. Then our static analysis identifies that this operation requires privileges. It injects, the compiler adds a request just before its execution for privileges, and then right after adds instructions to drop privileges again. The result is just this small section of code would actually execute with privileges instead of the whole application. So after doing the privilege overlay, or that operation, our security hardware is protected and enforcing DEP. Our sensitive I/O is also protected. And global data in your stack, you can no longer inject code to. They're read, write, and no execute. And then our code is set to read, write, providing code integrity. So you can't rewrite the code. So in addition to this privilege overlaying, we also provide stack protections by a technique called SAFESTACK. This was a technique that was developed and presented in OSDI in 2014. This protects against stack smashing. So the way it works is it does static analysis of the stack to identify variables that may be used in an unsafe way. any variable that could potentially be used in an unsafe way is moved to a separate stack called the unsafe stack. And we adapt this technique here to these small microcontrollers or bare metal systems. So the way we do that is the analysis runs, creating a stack and an unsafe stack. We invert the direction of the unsafe stack, so those two stacks grow away from each other. We then move the unsafe stack to the top of memory and place a guard region below it. So what happens now is if something overflows on that unsafe stack, it'll either hit this guard region, which will cause a fault, or it'll overflow the upper end of memory, which will cause a fault also. So we've now limited the variables that can cause corruption on the stack to just other variables that are also potentially unsafe, and preserving all of our stack pointers and other things on the regular stack. The last protection we apply is diversification. This protects against code reuse attacks and corruption of specific global variables. So EPOXY is given a seed when you compile an application. Based off that seed, it produces a unique binary, and that binary applies diversification in a couple ways. So first, to RAM, we have our layout here. What you'll notice is that while these systems are really constrained, this green area of memory is it's unused, but can be used. So what we do is we break that up into 5 sections, distribute those 5 sections throughout the rest of the application, providing random offsets to all of the regions. And then we randomize inside of the data sections and inside of the BSS section. So internally, every global variable gets randomized to new locations. So if you don't know, the data section is your initialized global variables. Your BSS section is all your 0 initialized global variables. So here we've randomized the locations at a fine-grained level for all of your global variables. We provide a random offset for both the unsafe and safe stacks. For code, which is in your flash, we randomize in a similar manner. We break up, we fill all of our RAM with jumps to a fault handler, which we add to the program. Then we randomize the functions so that all of the rest of the memory, if anything ever hits a piece of memory that it was not intended to be executed, it'll jump to this fault handler and we can decide how to handle it. So after applying all of those protections, the ones on the right I went over previously, the ones here on the left. So we've isolated unsafe local variables to the unsafe stack. We have protections on our global data. We have the stack protected against smash stacking attacks, and we have code reuse protections on both the stack and code. So I started out by saying that there's a lot of very tight constraints. We evaluated the runtime performance using Beebs benchmarks. This is a suite of 75 benchmarks for bare metal applications. So we evaluated the SS as SAFESTACK only, the middle one is privileged overlay only, and then all stacks is all the protections. So notice that on average we have very little overhead, and for power we also have on average very little overhead, and our variance isn't too high. We then evaluated 3 applications, 2 of which were provided by the vendor of our board that we ran our experiments on, and the other one, PINLOCK, we wrote ourselves. So we've got runtime and energy requirements. What you'll notice with PINLOCK, right, so most of them they're under 10% for all of the variants. We created 20 binaries with 20 unique seeds, and this is their runtime and overhead. You'll notice, so PINLOCK is bound, it's I/O bound, waiting on a serial port to input a pin. And so it has a very tight runtime distribution because most of any overhead's hidden by that I/O bound. However, there's a large distribution in its energy usage because what it's doing while it's waiting changes, or what it's executing while it's waiting changes slightly. We also used a ROP compiler to determine how many gadgets survive across 1,000 variants. So we created 1,000 binaries and then looked at how many code reuse how many ROP gadgets survive. So ROP gadgets is a short segment of instructions that end in a return, and an attacker can perform arbitrary execution by chaining together enough of these gadgets in the right order. They can execute whatever kind of execution they would like. And so for the 3 applications, we find, like in the worst case TCP echo, we have there's one gadget that exists in 2 binaries at 107. So if an attacker only needed one gadget, you could expect it to work maybe 10% of the time. And then we also look at the number of privileged instructions that are executed and compared to FreeRTOS MPU. So FreeRTOS is a lightweight operating system for these types of systems. They have a version of it that uses the memory protection unit to restrict access to code and data. However, if any part of a thread requires privileges, the whole thread has to be privileged. So the result is that most of the programs, there's something in every thread that needs some kind of privileges. So they're running in the 95%-ish range of privileged instructions, whereas we're getting down below 1% of the actual instructions that execute with privileges. The conclusion for EPOXY is it basically fast forwards bare metal application security several decades, applies state-of-the-art protections that are available on your desktops to the very constrained systems of microcontrollers while meeting their runtime, memory, and energy requirements. If you want to look at the code, it's on GitHub. So I can take a few questions now, and then I'm going to go into my Usenix talk if there's any questions.
Do you plan on using this in other operating systems too, or many operating systems?
So currently it only supports a single thread. Its implementation only supports a single thread. To support other threads, we'd essentially have to instrument the context switch so that it was aware of a little bit of state that we keep track of. But otherwise it should work.
You think you're going to deploy this at work?
I don't know if there's plans. I don't currently have plans. I haven't done anything with it for about a year. The follow-up, my next work kind of builds off some of the ideas that we discovered while working on the EPOXY. Okay, so the next work that I have is automatic compartments for embedded systems, or ACEs. This was presented this last week at the Usenix Security Conference. This was done by me, Nave, Dr. EPOXY, and Dr. Pyre. And so Dr. Pyre runs the HexHive here. He just recently moved to EPFL. And Dr. EPOXY runs the Dependable Computing Systems Laboratory in the ECE department. So problem statement is very much the same as EPOXY. These bare metal microcontrollers are used in IoT systems. They're vulnerable to cyber attacks. An interesting example of this is in 2007, Google's Project Zero announced, they released a write-up on some vulnerabilities they discovered in Wi-Fi system on a chips, Broadcoms, that essentially just by having your Wi-Fi on and being in range of a rogue access point, they could send it Wi-Fi frames that would take over control of the Wi-Fi system on a chip. And then once they got control of the Wi-Fi system on a chip, they were able to go into the application processor of a cell phone. So they're able to take over the application processor also by chaining together a couple vulnerabilities. So ACES is looking at legacy code in these things. So again, we're a compiler-based solution. So if you have source code, we can recompile that source code without changing it to apply some defenses. So these systems, as I said earlier, have no separation of privileges, no data execution prevention. So on the right, I've kind of depicted what one of these applications looks like internally at SAFESTACK. So you've got your application logic, kind of spans the whole application, and then you'll have some libraries that might do like image processing, your TCP stack, serial communications, some signal processing, and then those will sit on top of a hardware abstraction layer for a piece of hardware. So like the image processing library would connect to your camera through a hardware abstraction library. TCP would talk to your Wi-Fi radio, etc. And again, all the code's privileged. If there's a flaw in your image processing or in your TCP stack, it can take over your camera. It can mess with your signal processing. So our goal with ACES is to automatically create mini compartments, to take this application and break it up into its components, and to isolate those components from each other so that if there's a fault in one of them, that it doesn't propagate into the others, or that it's harder for an attacker to propagate from one part of the program into another. So we use static analysis to automatically infer the compartments using a policy. This separates the compartment, how the program's compartmented from how it's implemented. And with each compartment will have associated with it code, data, and peripherals. Related work, EPOXY I just went through. There's a manual technique called Embed Microvisor. This provides a runtime and API to put compartments into an application. So if you develop your application using this Embed Microvisor, you can manually partition it into compartments and isolate those compartments from each other. And another technique that was developed here at Purdue, actually by Dong Yang's group, is Minion. This creates thread level compartments. So it uses the threads in the operating system and isolates those threads from each other. The difference between theirs is they have a fixed algorithm, and ours we use a policy that enables flexible compartments to be formed. So more formally what a compartment is, it's a set of concurrently accessible memory regions and authorized control flows between them. So a compartment is going to restrict both control flow and what memory the application can use. So here I've got kind of a simple control flow of an application or call graph. It's got 4 functions: on button, take image, TX image, TCP echo. The green arrows being a call. So on button calls TX image. We're going to put those in 2 different compartments. So compartment A, compartment B. So what ACES is going to do is it's going to restrict the control flow so that in compartment A, you can only on button can call into compartment B, and there would be no calls from compartment B to compartment A. We're then going to put restrictions on the memory also. So this diagram on the far right depicts the memory. So up towards the upper end of memory, we've got peripherals, like your Wi-Fi, your camera, general purpose I/O, serial ports or UART. You've got your RAM, which will be split into regions, and then your code in the green. And off to the right, you've got A and B, and the columns on the right with the A and B indicate if there's a gray box, it means that compartment A can access the memory just left of it, or compartment B can access just left of it. So compartment A here could access the camera and the GPIO and RAM region 1, whereas compartment B could access all of the peripherals and access RAM regions 1 and 2. So to create the compartments, we're going to use static analysis to identify all of the code, data, and peripheral dependencies. And then ACES will ensure that all of these dependencies are maintained when it applies compartments. We'll then use a MICRO-EMULATOR to dynamically identify any missed dependencies. So it's impossible to perfectly statically analyze all the dependencies in a program because of the aliasing analysis problem. Essentially, you can't trace pointers. Sometimes you don't know what a pointer points to until you actually run it. So you can't always trace pointers. So we use a MICRO-EMULATOR to help fix up any of these things that we may miss that I'll explain in more detail later. Our compartments are code-centric, which means a function belongs to only one compartment. And then a policy simply determines how functions, global variables, and peripherals are grouped together to create compartments. We implemented 3 example policies: a naive file name policy, optimized file name policy, and peripheral policies. I'll explain what they are a little bit later. And then the memory protection unit is used to restrict access to memory regions. So to create compartments, there's 2 things we have to do. We have to, 1, identify what goes in what memory regions and the permissions for all those memory regions, and then the control flow between the functions. So first, I'll go through how we identify and put everything into the appropriate memory regions to meet the hardware requirements of the memory protection unit, and then I'll go through how we do the control flow. So the first thing we do is we build a program dependency graph. So on the left here, I've got an example program. The details of it aren't really important. The important part of it is it's got 4 functions. Those functions use some peripherals and some global variables. So on the right, the green arrows again indicates a call between the functions, and a black arrow means that that function reads or writes the global variable or peripheral on the right. So the orange being peripherals and the blue being a global variable. So after generating this using the compiler, we will transform this to a region graph. So for the region graph, essentially we're going to say we have as many regions as possible. There's no restrictions on the number of regions, and we're just going to map things to a region. So first, every function gets mapped to a region, every global variable gets mapped to a region, and then every peripheral gets a region mapped to it, one per each edge in the dependency graph. This is because their addresses are fixed in hardware and already satisfy the hardware requirements. And so each compartment can determine how it wants to access peripherals independent of all the other peripherals. Whereas with global variables, all of the compartments have to agree on how they're going to access global variables. So that'll become a little more clear as I go through this. So the next thing we're going to do is we're going to apply a compartmentalization policy. This defines what should be grouped together to form a compartment. We implemented 3 policies, a naive filing policy. So we just grouped functions and global variables together based off the file they were defined in. So if they were defined in the same file, they go in the same compartment. The optimized file mode takes that as a starting point, then looks at the program dependency graph and moves things to new compartments based on its connectivity. So every function gets moved to the compartment that it has the most connections to in the program dependency graph. And the peripheral policy, we look at the control flow graph and the dependency on peripherals. Any function that accesses a peripheral gets put in one compartment, and then we walk up the control flow graph, adding functions to those compartments until there's a conflict in dependencies, and that function could be dependent on more than one peripheral. And when that occurs, then we put those together into one compartment. So to illustrate some of the challenges with grouping everything together, I have an illustrative example that it's not actually one of those policies that I'll walk through with the diagram on the right. So here we're going to merge the TX image and TCP TX functions together, and global variables, global button and global image. After applying the policy, there could be some optimizations that can improve the security or improve the performance. So you may want to enforce, that certain things aren't grouped together for a security thing, or for performance that you can only have so many edges or some other transformation. Essentially, an optimization just takes the region graph as an input and outputs a different region graph, having modified it in some way. So here you'll notice that take image and on button have the same set of dependencies. So we merge them together into the same region. This would help performance as there'd be fewer compartment transitions. After optimizing it, we lower it. This is where we take the hardware constraints of the memory protection unit into consideration and make sure that this will actually work on real hardware. So to do this, the memory protection unit has only so many regions that it can enforce memory on. And so we have to reduce the number of edges each code region has to less than the number of available MPU regions. For this example, I'm going to use 3. Because we're merging things together, this can increase the privileges, so it's detrimental to security, or it affects security in an adverse way. So here we're going to first merging occurs iteratively until every code region is below their number of required dependencies. So global TX state and global TCP stats here get merged, and then we merge Wi-Fi and GPIO. And when we merge these two regions, what happens is their addresses are fixed in memory, so we also have to merge, there's peripherals between them essentially that also get added to that memory region. So by merging peripherals, sometimes we pick up additional peripherals that aren't even in the dependency graph. We then map this to memory. So each code region gets mapped to a code region and becomes the foundation of a compartment. And then each of the peripheral regions and data regions would determine the permissions shown on the right under A and B. So you'll notice that when we merged the Wi-Fi and GPIO, because of their locations and restrictions on the memory protection unit, we also picked up the camera and the UART. So after determining how everything should be laid out in memory and the permissions for memory, we have to restrict the control flow. So we do this using the compiler. We identify any function call that may traverse compartment boundaries and instrument those calls to invoke a compartment switcher. This compartment switcher executes with privileges, while the rest of the application executes without privileges. And the compartment switcher authenticates the transition in both ways. So essentially, what will happen is this call will only be allowed to call a specific function in the other compartment. And the compartment switcher, after authenticating the call or return, will switch the memory protection unit's configuration to enable the memory for the compartment that's being entered to be accessible. The final component of the design is this micro-emulator. So as I said earlier, the alias analysis problem prevents us from capturing all of the dependencies in the program dependency graph. And so the micro-emulator is a runtime. It's used in two modes. One is a profiling mode where it records the execution of benign runs. And from that recording all the accesses that are missed, we generate a whitelist, which is then compiled into an enforce mode. So what happens is when an access is made to a variable or peripheral that was not in a compartment's code regions, it causes a fault. We catch that fault and then check the whitelist to see if the write is allowed to go through. If it's allowed to go through, then in software we implement that write. We manually go in and write the memory and update all of the registers and all of the flags that we need to in the processor, and then we return from the fault handler to the next instruction. So to the regular program executing, it looks like the write went through, but really what happened is we executed 100 instructions to emulate all of the effects of that write. So this needs to be used very sparingly for performance reasons, but it also allows us to capture these dependencies that would be missed, and also to overcome some of the limitations of the memory protection unit. Yeah?
Is this during compile time or after compile time?
This is during runtime. The micro-emulator is at runtime. We also use it to protect the stack. So when you enter a new when you switch compartments, we make the previous part of the stack read-only, and then if anything needs to write to the previous part of the stack, it'll cause a fault. Micro-emulator will run, see if it's authorized. So we evaluated this using the 3 policies that I mentioned previously, and then we have 5 applications that run on an ARM Cortex-M M4 microcontroller. These applications are PINLOCK. They're very similar to the EPOXY work. So PINLOCK takes a pin over a serial port, hashes it, compares it to a saved hash. If it's correct, it turns on a light indicating that the lock had been unlocked. If it's wrong, then it gives you a certain number of attempts before it locks itself out. The other 4 applications were provided with the development board and exercise a number of different peripherals. So to evaluate the security, the first thing we did is a case study. So in this example, the attacker's trying to unlock the lock on PINLOCK. We assume that there's a write what where vulnerability in HAL UART receive. So this means the attacker from this function can write any part of memory they want. And then we look at how these policies would affect the impact of that write. So if the attacker's trying to unlock the lock, there's 4 ways he could do this. The first one is to overwrite the global variable storing the pin. The second one is directly write the IO, the GPIO, just basically writing directly to the peripheral and saying unlock the lock. The other one is a control flow hijack, where they directly call the unlock function. And the other one is a confused deputy attack, where they call a function that calls the unlock function with the correct inputs to make it think it should call the unlock function. So it's called a confused deputy because you deputize this other function to do your dirty work for you by confusing it. So the naive file name and the optimized file name policy protect against all 4, and the peripheral policy only protects against the GPIO attack. And this is because the compartment that has this vulnerable function on the peripheral one also has the global variable storing the pin, the unlock function, and functions which call the unlock function. We then did an evaluation of its runtime overhead. The big takeaway, so there's 5 applications. Each of the bars represents one of the different policies. The takeaway is based off the policy, you can have a small runtime impact from around 13%, 25%, to a very large overhead of 5.7x. and that the emulating instructions accounts for the largest portion. That's the tan box. Emulating instructions accounts for a very large portion of our overhead for the various policies. And then the blue and orange are compartment entries and compartment exits. So either calling into a compartment or returning from a compartment. Memory overhead. So we add a runtime to the applications. So memory, there's two overheads. There's overhead in flash, which includes our code, and overheads to RAM, which includes some state information that we save between switching compartments. So in flash, we have the code that we add for our runtime. Or sorry, that's the runtime. The blue, the code, is we instrument the code in the program, so it increases the code size. And then we add metadata, which encodes all of the whitelists and the valid targets for compartment switches. But the largest overhead, both in RAM and flash, is fragmentation. And this is caused by the memory protection unit requires that all of its regions be a power of 2 in size. And so every code and data region we have to pad out to a power of 2. And so this results in high overheads. The next generation of memory protection units does not have the power of 2 requirement, so that will go away. In flash, or in RAM, we add a compartment stack and a MICRO-EMULATOR stack, which is a few, like 600 bytes. So in conclusion, ACES applies least privileges to bare metal IoT devices. It doesn't require changes to the application logic, and it uses and works on existing hardware. It automatically enforces sub-thread level compartments and decouples implementing the compartments and the policy from the application, and will enable research in how to best create those compartments. It will also be available on GitHub as soon as it gets through review at Sandia. So I can take any questions on this. Yeah.
So it looks like you only have support for ARM. Are you planning on expanding to x86 at some point in the future, or is ARM right now because it's just microcontrollers?
So it's focused on microcontrollers, and we're using the memory protection unit, not a virtual memory or memory management unit. A lot of the analysis is when you get to really large programs for x86 might be intractable. So I don't have plans to take it to x86 at the moment, but some of the techniques might be applicable there. Yeah.
So you said the switcher was the thing that ran with privilege. So what if I was a bit confused. What if another instruction in one of your compartments required privilege? Does it go through?
So the way we handle that is some of the compartments have privileges. They execute with privileges. So
the switcher isn't the only thing always with privilege.
Right. So ideally, your program would have very few of these compartments. They're compartments that legitimately need to access the memory protection unit and other system functions.
My second question was so when you run the emulation, that's during runtime on the actual ARM processor, right?
Yeah.
So will that catch? Will it run the micro-emulation every time there's a fault, or will it run micro-emulation every time you execute an instruction, or when exactly is the emulation being run?
So the emulator would run when there is a write instruction, which tries to write memory that it doesn't have access to. At which point the whitelist is checked, and if it's authorized, the micro-emulator will run.
Cool. All right. So it's if there's a fault, it'll run the micro-emulation to see what it is, and if it's bad.
Yeah, if it's bad, it'll just stay in the fault handler. If it's okay, then it'll fix things up and let it continue.
Cool.
So the micro-emulator is essentially filling the gap, all the transitions you didn't catch during the static analysis.
Yeah.
Okay.
Yep.
How soon do you think it'll be up on GitHub?
I don't know.
Okay.
I don't know how long the process will take.
So did you write the static analysis tools yourself? Or
Yeah, so they're all based off use LLVM.
are they all going to be on GitHub?
Yeah. Okay, well, that's all I have.